Welcome back, guys. After the last two lessons, we've been introducing functions and looking at the graphs of functions, and now we're going to investigate one family of functions, the linear functions. We're very familiar with linear equations and linear functions, but let's investigate some more of their characteristics. So our slope-intercept form, as we are used to, is f of x equals mx plus b, where m is our slope and b is our y-intercept. Now, what's interesting about, or what's special about a linear function is that your slope, which is also our average rate of change, if you remember from our previous lessons, is always the same. So we say that it is constant. And this is one way that we can verify that a certain data set is linear by checking to make sure that we have a constant rate of change. So we have a table of values, and we want to determine whether or not this data set is a linear function. We can do that by graphing, but graphing takes quite a bit of time. So what we're going to do is investigate the slopes. First, I want to find the slope between the first 2 points. The slope formula, we'll write this up here, remember, is y2 minus y1 over x2 minus x1. And plugging in our data values, we have 1/2 minus 1/4 divided by -1 minus -2. Simplifying our numerator, 1/2 minus 1/4 is 1/4. And -1 minus -2 is the same as -1 plus 2, or 1. And this fraction just simplifies to 1/4. Next, we'll find the slope between the next two sets of ordered pairs. So y2 minus y1 over x2 minus x1. 1 minus 1/2 is 1/2. 0 minus -1 is 0 plus 1, or 1. And we see that we have a slope of 1/2. Since we don't have the same slope between the two sets of ordered pairs, this is not a linear data set. Trying another example. Between our first two data points, our slope is -3.5 minus -4 divided by -1 minus, let me fix that, -1 minus -2. -3.5 plus 4 is going to be 0.5, and -1 plus 2 is 1. We have a slope of 0.5. Remember that if you have decimals already in your problem, it's appropriate to leave your answers as a decimal. Otherwise, always use an improper fraction that's simplified. Between our next 2 points, our slope is -3 minus -3.5 divided by 0 minus -1. -3 plus 3.5 is 0.5. And 0 minus -1 is 1. So we still have the same slope. Just because we're seeing a consistent slope between the two first sets doesn't mean that this data is linear. Things could change in the next point. So we do need to make sure we check every set or every pair. So the third set, our slope is -2.5 minus -3 over 1 minus 0. -2.5 plus 3, so that 0.5 over 1. Things are looking good so far. We have one more set that we want to check. M is equal to -2 minus -2.5 over 2 minus 1. Which is, again, 0.5 over 1, or 0.5. Since we have a constant rate of change between these data values, we say this data set is linear. Going through examples like this will help us reinforce that slope formula. So there are 4 different types of slope. We have a positive slope, which is kind of like our uphill, our negative slope, which is our downhill. Remember that we're always reading our graph from left to right, so that's why I'm saying uphill, downhill. We don't want to read from right to left because then that can get confusing. A zero slope is a horizontal line, and an undefined slope is a vertical line. Now notice in these four categories of slope, none of them say no slope. Anytime you're dealing with a linear function, you have some slope. It's just either zero or it is undefined. So be very careful with that. Given f of x equals 3x plus 5 and g of x equals negative 2x plus 15, we're going to solve a couple problems. First, we want to solve where f of x equals 0. Again, this is just finding where y is equal to 0. These are also our x-intercepts. So solving algebraically, we get 0 is equal to 3x plus 5. Subtract 5 from both sides. 3x equals negative 5. X is equal to negative 5 over 3. So that's where our x-intercept is going to be. Solving where f of x is less than 0, when we think about connecting this inequality to the graph, we want to think about where are the y values of any function less than 0 or negative. And that is going to be below the x-axis. So when we get an inequality for this problem, that's going to tell us the values of x where my graph will lie below the x-axis. 3x plus 5 is less than 0. Subtract 5 from both sides. Divide both sides by 3. This is where x is less than negative 5 over 3. So to the left of negative 5 over 3, our graph will lie below the x-axis. Using the same functions, let's solve where f of x equals g of x. This is where the y value of this function is equal to the y value of this function, which is the same thing as their point of intersection. Solving algebraically, we have 3x plus 5 equals negative 2x plus 15. Add 2x to both sides. That way I have a positive coefficient on x. Subtract 5 from both sides. We have 5x equals 10. Dividing both sides by 5, we get x equals 2. So when we have an x value of 2, both f of x and g of x will have the same output. In part D, we're solving for f of x greater than or equal to g of x, which is asking where my function f of x lies above the function of g of x. Even though this is an inequality, we're going to solve it using the same steps we saw in example C. So I'm going to go through that quite quickly. And we find that our solution is where x is greater than or equal to 2. So to the right of x equals 2, we'll see that f of x lies above g of x. And what we'll do here is we'll start graphing these two equations, and this will just reinforce those concepts and the ideas that we are looking in parts A through D. So starting with f of x, I'm going to graph f of x in white. 3x plus 5. I have a y-intercept of 5. And my slope is 3, so I'm going to go up 1, 2, 3 over 1. Up 1, 2, 3 over 1. 1, 2, 3 over 1. I can also go down 1, 2, 3 over 1. Down 1, 2, 3 over 1. Be careful, make sure you're paying attention to the scale. Mine is going by 2s, so keep that in mind. I'm going to try to graph the nicest line here. And now in red, I'm going to graph g of x, negative 2x plus 15. So starting on the y-axis at 15, my slope is negative 2, so I'm going to go down 2 to the right 1. Down 2 to the right 1. Down 2, right 1. And connect those points. Now we can see if we look back at our previous answers, where did those two functions intersect? They intersect at x equals 2. That's this point right here. You guys can see that? Where was f of x greater than g of x? This graph in white represents f of x. So we said that it was to the right of 2, and if I look to the right of x equals 2, I have that white line above the red line. The cost C in dollars of renting a moving truck for a day is modeled by the function C of x equals 0.30x plus 25, where x is the number of miles driven. Find the cost of driving 60 miles. X represents the number of miles, so 60 is what we're substituting in for x. Using your calculator, simplifying this, we get our cost is equal to $43. If the cost was $60, how far did you drive? Now notice we're using that same value of 60, but now they're giving you the amount, the cost of that rental. So this is representing C of x, and we want to find how many miles, which is x. Solving this equation by subtracting 25 from both sides. 35 equals 0.30x. Divide both sides by 0.30. And we'll use our calculator to find this. We get x is equal to 116.67 or 116 miles. Now notice I rounded down because think about this. If I round up, I'm going 117 miles, which I have to pay for that little bit of extra mileage. But that's just for the practical application of this example. Obviously our normal rounding rules, we would round this up to 117. So here's our function still. We're still working with that cost of renting a moving truck. Suppose that you have $100 to spend. What is the maximum number of miles that you can drive? So 100 is our cost. We're solving just like we did before, 0.30x plus 25. 75 equals 0.30x, and dividing both sides by 0.30, x is equal to 250 miles. What is the domain of C of x? The domain represents our x values, which we know represent our miles. So what is the set of miles that we can drive? If we think about it, we can't drive negative miles, so our domain has to begin at 0. But where does it end? How many miles can we drive in total? Now that depends on if you use part C or not. If we're using part C, where we have a limit of $100, then our domain only goes to 250. However, if you're not capping yourself at $100, let's say you have an unlimited budget for this rental truck, then our domain will go from 0 to possibly infinitely many miles. Another application for linear functions is cost and revenue. Our cost function represents all the costs for materials plus any fixed costs. Now, the costs for materials are just the pieces that we're going to use to manufacture whatever the product is. Our fixed costs are costs that are not dependent on how many of this product I make. So think about a machine that we use to create, let's say, skateboards. Now, I pay for that machine once, and I can make as many skateboards as I want. I don't have to continue to pay for that every single time I choose to make a new skateboard. Now, our revenue function has to deal with the money that's coming in. Now, be careful because there is a difference between revenue and profit. Profit is what we always think about when we think about the money we put into our pocket. At the end of the day, what do we get to keep? But before we can take home any money, we've got to pay for all of our expenses. So that's the difference between revenue and profit. Revenue is just all the money that's coming in. Versus the profit is the money that you get to keep after you pay for all your expenses. Now, if we're a new company starting up, our big moment in this manufacturing of skateboards is our break-even point. Your break-even point is where you're finally not losing any money to make this product. Our break-even point is where your cost is equal to your revenue. Once you exceed the break-even point, that's when you start making a profit. So let's look at this example. As I stated earlier, let's start a company making skateboards. Let's say it costs $30 to make each skateboard for its materials. And let's say we invest $12,000 into making this skateboard, or into the machine to make these skateboards. So there are our fixed costs. If we sell them for $130 a piece, how many do we have to sell in order to break even? First, we want to come up with our cost function. What are the costs for making these skateboards? Well, each one is $30, so 30 times X, where X represents the number of boards we're making, plus we have our fixed costs of $1,200. Our revenue is the amount of money that's coming in, and that's based on the price that we sell them for. We're going to bring in $130 for every skateboard that we sell. If we set these functions equal to one another, we'll be able to solve to figure out where the break-even point is. So we get 12,000 is equal to 100x, and dividing both sides by 100, we get x is equal to 120 skateboards. So we need to sell 120 skateboards just to break even. It's not until we sell our 121st skateboard do we start making a profit. So we've seen some applications of linear functions. As we progress through the course, we're going to investigate other families of functions. But hopefully this felt pretty comfortable for us, and we'll see you next time for composite functions and inverse functions.